Now that we have the data representation, let's see how to actually fill this hash map with the keys and values from the query string. We have already used a trait to create some types from string slices. If you remember, in the method struct, we used the from str trait on the method, and this gives us this from str method that's used to convert a string slice into whatever type we want, in this case the method enum. But the from str trait unfortunately will not work for the case with the query string. Remember that the query string stores references and it needs a lifetime, but from str does not have a lifetime parameter. The documentation states that it can only parse types that do not contain lifetime parameters themselves. In other words, it can pass simple enums like the method, but it cannot pass references or structs and enums containing references. So we cannot use from str for our case. We will have to use the more generic trait, which is just the from trait. We have already used the from trait in the request. If you remember, this is how we were converting between different error types. So in here, we want to implement from, and we want to convert from a string slice for our query string. And again, we have to put a lifetime in this implementation block. Let's call it buff again. And we put this lifetime on the string slice we are converting from and on the query string that we get afterwards. And to implement from, we just have to implement the from function. It will take a string slice as a parameter. Let's call it s, and it will have the lifetime buff, and it will return a new self. Let's add an unimplemented macro at the bottom here, so that the compiler doesn't complain while we implement the function. Notice that we're using the from and not the try from trait that we did use for our request. The reason for this is that this conversion cannot fail. Pretty much any string would be a valid query string. So we would always be able to convert a string into a query string struct. On the top of our function, the first thing that we have to do is actually create an empty hash map that we will fill. So we want it to be mutable because we will add data to it. Let's call it data, and we create a new hash map by calling the new associated function on it. Now the compiler is complaining because it cannot infer the types for the hash map, as we can see in the error here. To fix that, we can actually create a new query string. And if we pass the data inside, we can also just delete this. And now the compiler can see that we are passing this hash map to the query string, and the query string expects a hash map that's generic over a string slice and a value, so it can correctly infer the type for this hash map variable. The next thing that we have to do is start reading this string and split it on the ampersands. Let me actually move this down here so it is easier to read. And to split a string on some pattern, there is a method called split. So we can call s.split. And in here we can pass any pattern that we want. In our case, our pattern will be the single character that's an ampersand. What split will do is it will return an iterator over all the substrings in the string slice separated by the pattern that we passed. So it will give us an iterator over this substring, followed by this substring, followed by this, and all of them to the end. And because it gives an iterator, that means that we can use a for loop over it. Let's call this a substring in the split. Let's define two variables for the key and the value with some default values. So by default, we want the key to be equal to the substring, and we want the value to be an empty string. The reason we do this is to handle the case with the key C here. We see that C is just a key, so the entire substring is only the key and it has no value. We also want to make these variables mutable, so we can assign new values in cases when there are values. The next thing to do is to look for an equal sign, and to do that we can use the find function. We have already used the find function for string slices, so if we call find, we can pass a pattern that we want to be searched. In this case it's an equal sign, and find will return an option that will contain the index of the pattern that we provided. So because it returns an option and we only care about the case when it finds the equal sign, we can use an if let to unpack this option, and we can say that if it was a sum wrapping an index, we name this index I, and now we can assign new values to the key and the val variables. So key will be everything in the substring before the index I, because as we see, for example, with the A, key is the string before the equal sign, which is the string A here, and value is everything after the equal sign, so that would be the 1 here. And looks like we forgot to put an equal sign here, and our value will be everything after, but we have done this already. We know that we can't just say I to the end because this will include the equal sign and we want to ignore it, so we have to say I plus 1. And we know that this is safe because the equal sign is only 1 byte, so when we say plus 1, we jump over the equal sign. Okay, we got the values for our key and our actual value. Now we have to check and see if this key already exists in the hash map. If the key exists and the value is of the single variant, we have to replace the value in the hash map with the multiple variant, and we have to create a new vector that will have the previous value from the single and the new value. The other case is if the key already exists and it is already of the multiple type. This is the simplest case because we just get the existing vector and we push the new value to it. The last case is if the key does not exist, which means that we have to insert a new value in the hash map and it will be of the single type containing only our value. The hash map provides a very powerful interface for modifying its values in place. That means that we can swap whatever is in the hash map directly. We do that by calling the entry method on the hash map. So if we say data.entry, we have to specify the key we're looking for, and this will give us back this entry struct, which is representing the actual key and value inside of the hash map. Now we can call the .or_insert method on the entry. What this will do is it will check and see if this key did exist, and if the key does not exist, it will put the value that we specify as a parameter to this function as the new value for this key. So this handles the case when this key has not been inserted before and we want to insert a new single value, and this single value will wrap the val variable. Okay, we have handled the case with the new key. Now let's handle the case with an existing key. There is another method that we can call. It's called endModify, and I forgot the dot in the beginning. The endModify method accepts a closure or an anonymous function as a parameter, and it will pass the value from the hash map to this closure. We can see here that it accepts a parameter that is generic, and this is the type of this generic parameter. It is a function. This is how anonymous functions are typed in Rust, and this function will accept a mutable reference to the value from the hash map. And in the description we see that it provides an in-place mutable access to an entry in the hash map. So we would be able to swap whatever is in the hash map with a new value. So to write a closure in Rust, we specify the parameters between two pipes. In this case, we will get the existing value from the map, and the closure can either be followed by curly brackets for a multi-line function, or it can be followed by a single expression similar to match arms that can either have curly brackets lines or just one simple expression. In this case, our entire closure will be one match expression over the existing value in the hash map. To make this a bit more clear, we can specify explicitly a type for the variable that the closure accepts. Rust does not force us to do so, but in this case, let's do it so it's clear what we're doing. So we actually get a mutable value here, and we want to match on this value and see if it is a single or a multiple. So let's handle both of these cases. It can either be a value single, or it can be a value multiple. And both of these are wrapping some values. If it is a single, it's wrapping the previous value. So let's name this previous value. And if it is a multiple, it is wrapping a vector. So let's call this vec. The multiple case is very simple because it is already a vector. We just have to push a new value to the end of this vector, and that would be the value that we have currently. So we see that to append to a vector, we can call the push method on it. But the single case is a bit more tricky. First, we have to create a new vector. So we do that by calling the new associated function. And I forgot the name, of course. Okay, so we can create a new vector, and then we can push to this vector. We can push the current value, and we can push the previous value. This is one way to do that, but it took us 3 lines to add the values, and it would be more lines for every other value that we want to add. Because of this, Rust actually gives us a special macro for creating new vectors with values. The macro is called vec, and whatever we put between the brackets would be added to the vector. So we want to put the previous value and the new value. Now the compiler will complain because it can't fully infer the correct types for the vector, but this will be fixed in a minute. Now we have to swap the value in the hash map from the existing one, which is a value single, to a value multiple. And the seemingly obvious way to do that would be to assign a new value to the existing variable, because it is a reference, right? And we can just inline the vector in here actually, so we can get rid of this line. Let's think about what's happening here. See that existing is a reference to a value. In other words, it is just a pointer. It will be easier to see it here. So existing is just some address that points to some memory somewhere. So this memory here is inside of the hash map. This is what we want to swap. But by assigning to the existing variable like this, we are not swapping this memory here. We are swapping this address here. We're just assigning a new address to a new value. To be able to swap the memory that existing points to, we have to dereference the pointer and assign to the memory address there. The syntax for dereferencing in Rust is putting a star before the reference. What we are saying now is follow the pointer and write this new value over whatever it was pointing to before. And before it was pointing to the single variant, and now we're swapping it with the multiple variant. but this is safe because, as we've discussed in the enums video, all the variants of an enum take up the same space. So we know that the multiple variant will fit in the space for the single variant. And I just noticed that there is a bug in the code. Here we are looking for an equal sign in the string that we get as a parameter, but instead we actually want to look in the substring. That would have been an annoying bug to debug later. With this, the from implementation for the query string is done. Now we have to go back to the mod.rs file and actually export the types from the query string module. So from query string, we want to export two types. We want to export the query string itself, and we also want to export the value. But because value sounds quite generic, we can rename this to query string value. And with this, we can go to the request, and here on top, we can import from super. We want the query string, and we want the query string value. Now we can swap the contents of the query string option. So it will no longer hold just a string slice. Now it will hold a query string that has the buff lifetime. And down here, it will obviously complain. So where we actually generate the query string, we have to call the query string from function and pass it the query string from the request. This is all we need to do for our query string, and I just realized that we don't need to import the value here because we're not going to use it. Now we can head to the console and see if our code actually compiles, and yes, everything compiles fine. So now we have a much better representation of the query string inside of the request.